Imagine standing at the edge of everything we know, peering into a darkness so ancient, so absolute, that our most powerful theories said nothing remarkable could exist there, and then something looks back. That is exactly what happened when the James Webb Space Telescope turned its golden mirrors toward the farthest corner of the observable universe, and what it found didn't just surprise astronomers, it cracked the foundation of everything we thought we understood about how the cosmos came to be. This isn't a story about a minor scientific update or a small tweak to an existing model. This is a story about a discovery so far outside the boundaries of what our physics predicted that the researchers who found it struggled to explain it in any conventional terms. And the deeper they looked, the stranger and more magnificent the picture became. To understand why this matters so deeply, you first have to understand what the early universe was actually like, because the conditions in those first hundreds of millions of years after the Big Bang were almost incomprehensibly hostile to anything we would recognize as structure or complexity. In the very first moments after the Big Bang, the universe was not a place of stars and galaxies and open space. It was an unimaginably hot, dense, violently churning plasma, a primordial soup of particles crashing into each other so rapidly that light itself could not travel freely through it. The universe was, in the most literal sense, opaque. For the first 380,000 years, photons were constantly absorbed and re-emitted, trapped inside this chaotic particle fog, and the cosmos was a featureless, blazing inferno with no structure whatsoever. Then something changed. As the universe expanded, it cooled, and around 380,000 years after the Big Bang, temperatures dropped enough for electrons to finally combine with protons and form the first neutral hydrogen atoms. This moment is called recombination, and it was the first great turning point in cosmic history, because suddenly light was free to travel. But this freedom came with an unexpected consequence. The universe, now filled with this vast neutral hydrogen gas, became a different kind of dark. Not the dark of a hot plasma, but the dark of a cold, empty, silent fog stretching in every direction for hundreds of millions of light years. There were no stars, no galaxies, no points of light anywhere in the cosmos, just an expanding, cooling, yet featureless void of hydrogen and helium drifting apart in the silence following creation. Astronomers call this era the cosmic dark ages, and for a very long time our models told us it lasted far longer than we were comfortable with. The standard picture painted by decades of cosmological simulations was clear and consistent. Gravity would slowly, patiently pull that primordial gas together into clumps. Those clumps would gradually collapse into the first small, dim, chemically simple proto-galaxies. The process would be gradual, orderly, almost gentle. The first recognizable galaxy-like structures wouldn't appear until roughly 400 to 500 million years after the Big Bang, and even then they would be faint, primitive, and chemically bare, containing almost nothing beyond the hydrogen and helium they were born with. This was the expected story, a slow and predictable dawn following a long and silent night. The James Webb Space Telescope was built in large part to look back far enough to witness that dawn for the first time, to see those first faint flickerings of light emerging from the darkness. And it did. But what it actually saw when it got there completely rewrote the script. As part of an ambitious observing program called JDIS, an international team of astronomers pointed Webb at a tiny, seemingly empty patch of sky and looked as deep as the telescope could reach. They were hunting for the faintest, reddest smudges imaginable, objects so distant that the expansion of the universe had stretched their light far beyond the visible spectrum and deep into the infrared, which is precisely the wavelength range that Webb was engineered to detect. And in January of 2024, they found something that stopped the entire scientific community cold. A tiny, faint red object that they named JADES-GS-Z14-0. When they measured its redshift, the number that tells astronomers how far away and how far back in time they are looking, the result was almost unbelievable. A redshift of 14.32. That number placed this object at just 290 to 300 million years after the Big Bang. Webb had done it. It had genuinely peered through the cosmic dark ages and captured light from the very dawn of the universe, light that had been traveling for over 13.5 billion years before finally landing on Webb's detectors. But here is where the story takes its first sharp and shocking turn, because this galaxy wasn't what anyone expected to find at that distance. According to our models, a galaxy at 290 million years old should have been small, dim, barely there, a faint whisper of early star formation just beginning to stir. Instead, JADES-GS-Z14-0 was blazing. It was astonishingly, almost impossibly luminous for its age, glowing far brighter than any simulation had predicted a galaxy at this stage of cosmic history should be able to glow. And it wasn't alone in that brightness. Webb was beginning to reveal across multiple fields of view that bright early galaxies were not rare exceptions. They were more than 10 times more numerous than pre-Webb observations and theoretical models had suggested. Something about the early universe was fundamentally more productive, more efficient at building complex luminous structures than our physics had told us. But the brightness was only the beginning of the mystery. The real shock, the discovery that moved the conversation from surprising to genuinely stunning, came when astronomers analyzed the spectral light from JADES-GS-Z14-0 in detail, looking at the specific wavelengths of light that act as chemical fingerprints, telling scientists exactly what elements are present inside a distant cosmic object. What they found embedded in the spectrum of this 290 million year old galaxy was oxygen. Let that land for a moment. Oxygen in a galaxy that had barely had time to form at all. The Big Bang itself only produced 3 elements in any meaningful quantity: hydrogen, helium, and trace amounts of lithium. Every other element on the periodic table, every atom of carbon, nitrogen, oxygen, iron, gold, and everything else was forged inside stars. Stars synthesize heavier elements through nuclear fusion across their lifetimes, and then they scatter those elements across space when they die in supernova explosions. This process takes time. A massive star might live for a few million years, and then its death seeds the surrounding gas with the heavy elements that become the raw material for the next generation of stars. To find oxygen in a galaxy just 290 million years after the Big Bang means that at least one full generation of massive stars had already been born, had lived their entire lives burning through their nuclear fuel, and had died in catastrophic explosions, enriching their host galaxy with heavier elements, all before this light was even emitted. One researcher described it perfectly. Finding oxygen this early is like walking into a nursery and discovering a fully grown adult. It simply shouldn't be there by any conventional timeline we had constructed. And then, just as astronomers were still processing the implications of JADES-GS-Z14-0, Webb broke its own record. In a follow-up survey searching for even more distant objects, astronomers confirmed a galaxy that pushed the boundary even further back into the cosmic dawn. This object, designated M-Z14, had a confirmed redshift of 14.44, placing it at just 280 million years after the Big Bang, and making it the most distant object ever spectroscopically confirmed in the history of astronomy. 10 million years earlier than the previous record, 10 million years deeper into the dark ages than any human instrument had ever seen. And once again, It defied every expectation. MOM-Z Tween was compact, roughly 400 times smaller than our Milky Way, but its luminosity was extraordinary for an object of its age, radiating light at an intensity that had no business existing at that point in cosmic time. It was undergoing a massive burst of star formation, a furious, almost violent episode of stellar birth that was producing enormous numbers of new stars at a pace our standard models of early galaxy formation simply cannot accommodate. But as with JADES-GS-Z 14-0, the brightness was not the most troubling part. When researchers examined MOM-Z14's chemical signature, they found not just heavy elements, but a particularly striking overabundance of nitrogen, a specific chemical fingerprint that raises questions that our current models of stellar physics struggle to answer. Nitrogen in these quantities, this early, requires either stars of extraordinary mass, far beyond what standard stellar physics predicts should form in abundance in the early universe, or an environment so dense and so turbulent that star formation was accelerated to rates we have never witnessed anywhere else in cosmic history. Even more intriguingly, this specific nitrogen signature is also detected in the most ancient stars found within our own Milky Way, the so-called metal-poor stars in the galactic halo that formed in the very earliest epoch of our galaxy's history. This suggests a potential link, a thread of chemical continuity connecting the conditions in the cosmic dawn to the oldest stellar relic sitting right here in our own galactic backyard. The paper announcing MOM-Z14 used a phrase that is almost never seen in scientific literature: cosmic miracle. Not as hyperbole, but as a genuine acknowledgement that what they had found had no comfortable home within any existing theoretical framework, and the scientific community is now scrambling to construct new ones. Several competing ideas are being explored with urgency. One possibility centers on population 3 stars, the hypothetical first generation of stars in the universe that formed entirely from pristine hydrogen and helium with no heavier element contamination. Our models assumed these stars would be large, but still within a range that our physics could describe. But the evidence now building from Webb's discoveries suggests that population 3 stars may have been dramatically more massive than we imagined, potentially hundreds of times the mass of our sun, burning through their fuel at an incredible pace and dying in explosions so energetic that they could seed entire galaxies with heavy elements in a fraction of the time we assumed was necessary. Another possibility involves the dark matter, halos that serve as the gravitational seeds around which galaxies form. Our standard model of dark matter predicts these halos grow gradually through mergers over time, but perhaps dark matter behaves differently than we assumed in the very early universe, collapsing more rapidly and more efficiently than our simulations capture, providing the gravitational scaffolding for galaxy formation to begin earlier and proceed faster than any model has yet reproduced. There are even more exotic ideas circulating at the edges of theoretical physics, including theoretical objects called dark stars, powered not by nuclear fusion like ordinary stars, but by the annihilation of dark matter particles within their cores. These objects, if they exist, could in principle produce extraordinary luminosities without producing the conventional chemical signatures of normal stellar populations. However, the specific elemental abundances found in MOM-Z14 strongly suggest its light is produced by genuine stellar populations, meaning dark stars alone cannot be the full explanation, though the fact that such exotic proposals are being seriously discussed tells you everything about how dramatically Webb is stretching the boundaries of established astrophysics. What makes all of this even more consequential is that JADES-GS-Z14-0 and MOM-Z14 are not isolated anomalies. Webb has now identified over 100 candidate galaxies at redshifts greater than 10, a population so large and so consistently bright that it cannot be explained by statistical outliers or measurement errors. This is a systematic, repeatable pattern of observation that no current version of our cosmological models predicts or reproduces. There is a genuine and growing chasm between what our theories say should exist in the early universe and what Webb is actually finding there. And that gap is widening with every new observation cycle. The implications extend beyond galaxy formation alone. These early bright galaxies were also the agents of cosmic reionization, the great transformation that ended the Dark Ages and made the universe transparent. The intense ultraviolet radiation pouring from these early stellar powerhouses burned through the neutral hydrogen fog that had blanketed the cosmos since recombination, carving out expanding bubbles of ionized, transparent space that grew and merged until the entire universe became the open, light-filled cosmos we inhabit today. Understanding these galaxies means understanding how the universe escaped from its own darkness, which means Webb is not just rewriting the story of galaxy formation, but rewriting the story of how the observable universe itself became observable. What stands out most powerfully when you step back and look at the full picture is this: every major prediction our cosmological models made about the early universe has been contradicted by what Webb has found there. Galaxies were brighter, they were more numerous, they were chemically enriched far earlier, they were more structurally complex far sooner. The neat and orderly timeline of cosmic dawn that decades of theoretical work had constructed is not just incomplete, it appears to have been fundamentally wrong in ways that we are only now beginning to measure. And that is not a cause for despair in science, it is a cause for extraordinary excitement. Every civilization in human history has looked up at the night sky and wondered how it all began. We built the James Webb Space Telescope as our most powerful attempt to answer that question, and in the first few years of its science operations, it has not given us simple confirmation of what we already believed. It has given us something far more valuable, genuine surprise. The universe, it turns out, was far more industrious in its earliest moments than we ever dared imagine. It built brilliant galaxies, forged heavy elements, lit up the darkness, and began assembling the chemical building blocks of complexity with a speed and efficiency that our finest simulations never predicted and still cannot fully explain. The darkness of the cosmic dawn was not the empty, featureless void we assumed. It was already alive with furious activity, burning with the light of stars whose existence challenges everything we thought we knew. And here is the question that should stay with you long after you finish watching this. If the universe managed to build all of this complexity, this chemical richness, this structural sophistication in just 280 million years, what else might we have gotten wrong about the timeline of cosmic history? What other milestones, what other thresholds of complexity happened far earlier than our models predicted? And if the building blocks of chemistry were present that early, what does that mean for the conditions necessary for life itself to eventually emerge? The secrets hidden for 13.5 billion years are finally coming into the light, and the universe is proving to be stranger and more magnificent than we ever had the imagination to predict.